Okay, Math 31s. Today we're going to do lesson 4.3, the first derivative test. Basically, we've already covered all the stuff that we need to know for this. We're putting basically the first two lessons together, and this is going to be what's going to be included in our next unit, which is going to be curve sketching. So what is the things that we've learned? Well, we've learned that with our function, if we're given a graph, we can have a local maximum. We can see that our slope is increasing right here, so we would say something like f prime of x is greater than 0. Right here, we would see that f prime of x equals 0. We have a slope that's decreasing. We can say f prime of x is less than 0 here. Again, we have another f prime of x is equal to 0, and you guys get the idea. So what this means is we can now say that the function is increasing on the interval if f prime of x is greater than 0. We can say that the function is decreasing on an interval if f prime at x is less than 0. And we can say that it is going to have a local max or min when x is equal to c if f prime at c is either equal to 0 or undefined. That is what the first derivative test is. Sorry that the slide is blurry. This is in your notes in your workbook, so you can have a look there. But what it's saying is we need to always find our critical values or our critical numbers. So what we also need to see is that a local max is going to go from an increase to a decrease. That's where it's going to happen in our interval charts when we're looking at it. And a minimum is going to happen when we go from a decrease to an increase. Okay, so that's what we're going to be looking for. It does not change a sign at C, so there's no like peaks or valleys is what it's saying. It has concavity or a point of inflection. Okay, and what a point of inflection or concavity is something like this, where it changes shape. So here is a chart just describing how we'll have a local max or a local min, and it's just comparing when your prime of x is less than 0, but then it changes to greater than 0. That is where we're going to see the change. This is what we're talking about of inflection points, and that there's no change here. Now, to algebraically find our local max or min, we're just going to go through a few of the steps that we've been going through. So step number 1, find your f prime x and critical values. Okay, so just like we've done for the last two lessons, whenever we're starting to do any type of graphing or find any information about a function, we always just take the first derivative. So f prime of x is equal to 3x squared minus 3. Now our part of this step is to find our critical values, and because this is a cubic function, we're only going to have where it equals 0 and is not undefined. So 0 is equal to 3, factor out our 3, we get x squared minus 1. 0 is equal to 3, x plus 1, x minus 1. And we're now going to see that we have two critical values, x is equal to 1 and negative 1. So just like before, we're going to check what happens with our function at 1 and negative 1. We already know that our slope is 0, so we know a change is happening. But what is it? Is it a local min or a local max? So we're going to set up our interval chart, so that's step 2. And so we're going to go, there's no restrictions on this domain, so I'll mention that it's all real numbers. And so we're going to go from negative infinity to negative 1 to 1, and then 1 to infinity. And we're just going to check what's happening. If this was a closed interval, we would only go to those endpoints, usually labeled A and B, and we would check those endpoints as well to see what's happening. But for here, we're just going to pick a number less than -1, so let's say it's -2. When I plug it into here as -2, I'm going to get a negative and a negative, which makes it positive. So it's actually going to be increasing. When I pick a number between -1, like 0, I'm going to get +1 and -1, so it's a negative and it's decreasing. And then I pick a number like x is 2, and we're going to get a positive times a positive, which is increasing. Now I know that this pattern goes increase, increase, decrease, increase. That won't always happen, especially when we start our chapter 5. But what it does show us is that if we're increasing and then we're going to a decrease, we have a local max here. And that's going to happen at that critical value, which we stated was -1. And then over here, we're going from a decrease to an increase. So right here, we're going to have a local minimum. And that's going to happen at x is equal to 1. And that just gives us some information about our graph. Now, if we wanted to actually find what the values of that max and min are, I have to go back to the original function. And my local max, I'm going to plug in where we said it happened, which was -1, and I'm going to get -1 cubed minus 3 times -1 plus 1, which is -1 plus 3 plus 1, and so we're going to get +3. So that is our local max. F of x is equal to 3. Now our local min, we're going to put in our +1. We get 1 cubed minus 3 times 1 plus 1. So we're going to get, what is that? -1. And so we have a local 1 and our local maximum at +3. And that's all we need to do. This helps us this chart helps us prove where the local max and min happen. So it's nice to show. Now when we have something just a little bit more complicated, something like this one, again, step 1, we're going to find our first derivative. Keep in mind, our domain is x has to be greater than or equal to 0 because of this radical. So we want to keep that in mind when we go and solve this stuff. Now we get a first derivative of 2 minus 4 times a half x to the power of -1/2. So the derivative of that radical. It's not a product rule because 4 is just a coefficient. So here I'm going to get 2 minus 2x to the power of -1/2. Now to find my critical values of a radical, what I like to do is I like to write it first as a radical. And now my domain of this one is x cannot equal 0. But I'm going to make that common denominator by multiplying this by root x. I still have my -2 and it's all over root x. So that's what I'm going to see. I can factor out a 2 here on the top and write it as root x minus 1 over root x, but nothing cancels. So we always want to pull it together because now we can see we have critical values at x is equal to 0 because that makes the function undefined. So something might happen here. It could be a max, it could be a min, or it just might not work. It might just be undefined in general because we know that the domain here, it can equal 0. So there could be something happening there. Now my numerator gives me my second critical value. When does root x minus 1 equal 0? Well, I move the 1 to the other side, I square both sides, and x is equal to 1. And so that's my other critical value, which makes the whole function equal to 0. So now I'm going to take my two critical values, which is x is 0 and +1, and I'm going to set up my interval chart. So I know that it is from 0 to 1, and I can't go less than 0 because it doesn't exist, so I don't need to include it in my chart. And then I know I can go from 1 to infinity. So I just have two of these. Again, I'm going to take a number from 0 to 1. Let's say I pick 0.5. 0.5 here in the denominator is a positive. 0.5 here just gets smaller. Minus my 1, it's going to be a negative value. So it's decreasing. I pick a number greater than 1. Let's say I pick 2. I'm going to get a positive minus 1 over a positive. This is one where you're going to want to be careful with your values. If you need a calculator to just check what root 2 is, minus 1, it's still bigger than 1, so it becomes a positive value, and it's increasing. So what we know is f at 1, it goes from a decrease to an increase, so it's a local minimum. Now how do I find my value? Well, I plug it into my original equation, which is 2 times 1 minus 4 root 1, which is going to be negative 2. So I have a coordinate that's really important for this function, which is going to be 1, negative 2, our local min. If I wanted to graph this to give you an idea of what it looks like, we have 0, 0 as a coordinate. We now have 1, negative 2 as our minimum. We have a x-intercept over here at positive 4, and my graph just does this. And you can see that this is the lowest part of our function. Okay? Because the graph keeps going up, this is also an absolute minimum because we can see it graphically. We can see it that it is going up forever, and that's the lowest point for this function. You don't need to know that it's an absolute minimum unless it is a closed interval. So we are only going to be working with local max or mins unless it's a closed interval. So I want to do one more with you guys, which is just another polynomial kind of question. Let's just go through it. This one just has a few more critical values, so maybe a few more max and mins. So if I take this function and I find my first derivative, I have 4 times my 3/4 that's already there, reduce my exponent by 1, minus 3, bring down the 3x squared, minus 6 times 2, x reduce it by 1, plus my constant. My 4's over here cancel. I'm just left with 3x cubed minus 9x squared minus 12x. Again, I have a common factor of 3x, so I'm going to take that out. I'm left with x squared minus 3x minus 4. I now can factor this. I get x minus 4 and x plus 1. And I have 3 critical values. Sorry, I should have made this all equal to 0. I'm going to have x is equal to 0, 4, and negative 1. So we'll set up our interval chart, and the interval chart is more a proof. Obviously, we can plug in all 3 of these values and then check the y value of whether it's a max or a min. But when we get into our next unit, the interval chart is really helpful. So it tells us a lot of information. Again, there's no restrictions on this domain. It's just all real numbers. So I'm going to go from negative infinity to negative 1, then negative 1 to 0, and then from 0 to 4, and then 4 to positive infinity. I'm checking what is happening to my slope to give me information about my original function. So I pick a number less than negative 1. I always like to look at it in this factored form. So I plug in negative 2. I get a negative and a negative, which is, negative 2. I get, there's a third one, negative 2. So a negative times a negative times a negative is negative, and it is decreasing. The second one, I pick something between negative 1 and 0. This is going to be a positive. It's increasing. And you can pause me at any point and try the question itself as well to find the values that you're getting. Okay, here we get a negative, it's decreasing, and here we get a positive and it's increasing. And so what did we find? We found that from a decrease to an increase, we have a local min right here, and increase to a decrease, we have a local max. And then over here, decrease to an increase, again, we have another local min. And that is it. We plug them back in. So at f is negative 1, we get negative 1/4. At f is 4, we get negative 94. And f at 0, we get 2. And those are the values of our local mins and our local maximums. And that is it. Your homework, I'll put it on there so you can pause the screen and check it. And hopefully the sound was a little bit better for this one.